So this is going to be the index of today's session. First, we'll have the introduction on the product. Then we'll see some features of geometry modeling, meshing properties, boundary conditions, loads, uh, types of analysis, post-processing features, and in the last, the Q&A session. So about Midas GTS, Midas GTS is an all-in-one and it's a complete finite element analysis package which has been developed for the structural analysis of geotechnical and tunnel engineering problems. So in our product, we offer you the 4 benefits, namely convenience, rapidity, accuracy, and productivity. Convenience comes from very user-friendly GUI, and rapidity comes from an intuitive menus which helps in a rapid modeling, and accuracy comes from tested solvers, and this leads to overall productivity. So regarding the application areas, the application areas includes deep foundations and soil structure interaction problems, unconventional tunnel intersections, excavations or embankments or other slope stability problems, then groundwater flow and coupled analysis, and vibration analysis for the earthquakes or blasting problems, and many more. So in the application areas, here we have deep foundations and soil structure interaction, where we can model, where we have modeled pile raft foundation for a high-rise structure, or deep excavation and temporary structures. And also we can consider the unconventional tunnel intersections in the 3D modeling. And we can also consider the shield TBM analysis. For the dynamic part, we can consider the vibration analysis for the earthquake and blasting. And we can also consider underground structures, for example, subways or disposal facilities. One more application area is groundwater flow and coupled analysis problems, where we can also do coupled analysis of stress and seepage. And in the last, slope stability and embankment problems, including the cut slope or reinforced or unreinforced slopes. So in the company benefits, the 3 major benefits are time efficiency, which comes from rapid modeling and very intuitive user interface, and increased productivity due to these enhanced features and an accurate solver, plus generation of quality reports, which saves the laborious job of creating reports or recreating the reports when we have made some iterations in the model. So these 3 main features are backed by our powerful pre and post processors, user-friendly interface, development which is guided by our users' feedback, technical support 24/7, and a reliable solver. So here we are seeing the GUI of the GTS. So first we have here is the workstream window. Workstream window is a window where the modeling history gets updated, and it includes the geometry options, the properties, material properties, the loads condition, and the boundary conditions. So the workstream window automatically gets updated when we proceed with the modeling. And also, according to the option, we can choose or we can perform certain operations. And then we have property window. In the property window, if we choose a particular option in the workspace window, then for that particular option, all the essential features are displayed in the property window. So as you are seeing here, if we are seeing the ground material property, then the all ground material property data is shown in this window. Then work window is the plane or space where we perform our modeling. And task pane window is the window which has been developed for the ease of user while modeling. So it enlists all the essential processes or steps which you have to take for modeling. So it includes defining the material properties, loads conditions, boundary conditions, analysis cases, and so on. And then we have the table window for inputting the data or modifying the data. And then we have the output window where the messages during the execution of the functions are displayed. Then we have main menu where all the functions or the options are enlisted. Then we have a standard toolbar for performing the standard operations. Then the selection toolbar for selecting single or multiple entities. Then we have the workplane toolbar for selecting a workplane or switching it. Then we have the snap toolbar for using the snap options while doing the geometry modeling. Then we have a tab toolbar. This toolbar again has been developed so that the users are able to model their projects rapidly. So this toolbar has almost all the essential functions which are present in the main menu, but here they are present in the icon. So this provides a quick and easy access. View toolbar. In the view toolbar, we have the options for the rotations or viewing a certain plane, let's say a top view or a side view. And also there are tools for measuring distances. So again, it's all for the ease of the users. Here's the measure toolbar. And then in the end, we have the unit systems. So the unit systems can be changed or modified at any time during the process of modeling. So when we have created our model, then in GTS, there is an options for viewing our model, whether it's a mesh or a solid, in different display modes. So here we are seeing a mesh, which is by default shown in the shading option. But according to our requirement, we can also see the mesh in a free face wireframe or a feature edge with shading. Now we'll proceed to the geometry modeling. So the purpose of geometry modeling is that if we have 2D geometry in a plane or a 3D geometry, let's say solids, then our next target is to generate mesh using the various features in our product. And the mesh accordingly can either be in 2D or 3D. So before we begin with the geometry modeling, we first need to understand the hierarchy of geometrical entities in GTS. So to begin with, we have point. Point can either be in 2D or 3D space. And then we have curves. Curves or edges, they basically join or connect 2 points. Then we have a surface. A surface is bounded by multiple curves. And then we have solids. In solids, it's similar to a surface, but again, it has a volume. And the compound is the highest order shape in the geometry modeling. So as you can see here, for curves, we have 2 points and a surface, which is a rectangle here, then at the vertices. And same for the solids, we have points at the vertices. Then one more very essential feature in GTS is that imprinting point. So if we consider a situation of modeling piles, then for proper nodal connectivity, we need to have a proper connection between the pile tip and the ground mesh. So we can do this by an imprinted point option. If we do not use this option, then there would be no proper nodal connectivity, and the piles would just be hanging in the ground mesh, and that would be an incorrect modeling. So again, this is a very essential feature. Curve. An edge. If you have a line or a curve, it connects 2 points, and a wire is a group of continuous edges, and a face is enclosed by multiple edges or wires, and a solid is enclosed by multiple faces, and again it has a volume. So as we'll see here, that we have edges and wire is a group of edges, and we have a face bounded by multiple edges, and solid is bounded by similar faces, and it has a volume. In surfaces, we can generate planar surfaces or a grid patch using the grid data and inputting the elevation, or a vertex patch inputting the 3D coordinates. We can also generate a Coons patch or a NURBS patch. The difference between Coons patch and NURBS patch is that for Coons patch, between 2 or 4, we can choose or have any number of curves to generate the surface. But for NURBS patch, we need to have an enclosed domain for generating the surface. Then we have primitive solids, which include cylinders, cone, box, sphere, torus, or wedge. And then going to some of the geometry operations, we have translate, which is used to translate or duplicate the elements with respect to a direction. So if we have a face here, then we can translate with respect to the y direction, and we can also generate uniform copies as being shown here. Then rotate. We can rotate a shape with respect to a rotation axis. So if we have a face here, then we can rotate it with respect to the vertical axis and obtain a profile like this. Then mirror. Mirror is basically used to translate shape with respect to a mirror plane. So if we have a symmetrical situation, then rather than modeling or rather than creating the geometrical entities time and again, we can use the mirror option, and we can generate our geometry at a very fast rate. So this is an automation feature. So let's say we have a solid, then we can quickly mirror it with respect to a mirror plane, YZ plane, and generate a mirror shape. And this is a very quick process. Then scale. Scale is used to change the size of the selected shape. We can either scale up or scale down. So if we have a shape here, a face, then we can use the scale option to scale up or scale down. Then one of the most important features in geometry modeling is extrude, and this option is used to extract a shape in a direction. So uh, if we are creating a solid, let's say, which is not covered in the primitive solids database in our product, then we can create a wire as shown here, and then we can simply extrude it to obtain a solid profile. Then rotate, similarly to the previous part, we can rotate the revolution profile to create solid, shell, or face. So here, rather than just rotating or moving the shape, we can actually create solids or shells. So here we obtain a torus. This is a revolved solid. And then in loft, we can create a shell or solids between two dissimilar profiles. So if we have two profiles, dissimilar profiles, then we can perform a loft operation and create a smoothly varying solid for these two profiles. Then in sweep we can extract selected profile by following a guide curve, and by this operation we can create face, shells, or solids. So if we have our profile and if we have our guideline, then by using this function we can obtain a sweep solid. In Sue, if we have a group of two or more faces, then we can use this option to convert these faces to form a single shape. So if we have two faces as shown here, then by using this function, we can generate a one shell having two subfaces. So it's a single entity after the operation. Then going to the solid modeling. So in the first figure, if we have a solid and if we use the trim function, then by using this function, we can trim the solid with respect to a surface, and then we can also remove the one of the trimmed part of the solid. And in the divide part, uh, here we can divide our solid with respect to a surface, and the advantage of trim part is that if we have a surface which represents the actual ground contour, then we can simply create a solid representing the ground mass using one of the primitive solid, and we can simply trim that solid with the surface, and the trim solid would eventually have the profile of actual ground. And then we have divide by multiple surfaces. This is one of the most important features in geometry modeling. So in this particular case, this represents a case of a tunnel which is embedded in ground. So doing the construction stage analysis, if we wish to use our elements, or if we wish to create a segmental construction, then we can divide our solid, which is the main tunnel solid, by multiple surfaces, and then we can accordingly activate or deactivate them in the construction stage. And then we have the Boolean operations. So for any given two solids A and B, we can perform a fuse operation, meaning fusing both the solids, or if we perform the cut operation, then we can cut the shape of the tool solid from the main solid. And then if we have a common operation, then the common part between both the solids will be kept after the operation. So here the function of trim solid will be more clear. So in the trim solid, we can divide a solid by surface, and we can also remove the divided solid with respect to a reference point. So if we have a solid like this, then we can divide it with respect to a trim surface, and then with respect to a reference point, we can remove the solid. In dividing the solid by surface, so if we have a solid as represented by this frustum, then with the tool surface, we can divide the solid to obtain two different solids. Embed function uh, embeds one solid into another solid. So this feature is again, as shown here, is a very handy tool for modeling underground structures. So if we have, let's say we have want to model a tunnel, an underground tunnel, then we need to have proper nodal connectivity between the tunnel, the mesh sets representing tunnel, and the mesh set representing the ground. So to ensure that, we use this embed function. So if we have a tool object and a master object, then we use this option to embed the tool object into the master object as shown in the highlighted orange part. Then we have modifier features, amongst which the first is trim surfaces. So if we want to manually perform this operation, we can trim two surfaces. So the practical application could be a tunnel with the connecting gallery. So if we have shotcrete linings for both these parts, then we can trim the unnecessary part of the connecting gallery shotcrete by using this function. The offset function is used to provide an offset to the mesh, and in the chamfer we can provide a smooth transition between the shapes. The local prism is a powerful tool for creating 3D geometry, and whereas the draft function is used to create edges in a 3D modeling. Then in explode, by using this option, we can disassemble a higher order shape into lower shapes. So if we have a solid, then in this particular example, we can explode it to get faces. And then co-shapes. Co-shapes are the same shapes which exist on the same location. So if we have two faces, then if we check for the duplicate, then we'll obtain a co-edge. And if we have two neighboring solids, then we'll observe a co-face. So the advantage of having co-shapes and co-faces will be more clear in this slide. So if we have co-faces, let's say the top and the side part, then co-shapes actually ensure proper nodal connectivity between two mesh sets. So if we have two solids and if we have proper co-faces between them, then there would be proper nodal connectivity. But on the other hand, if we have a co-face only on the top part but not on the side part, then here we'll have improper nodal connectivity, and this would obviously be an incorrect modeling. So this is also an essential tool for modeling. Then we have a powerful tool known as Terrain Geometry Maker. What this tool does is that if we have a digital map representing the actual ground contours, then in the form of DXF format, then we can import this data and generate a surface representing the actual ground contours, and subsequently we can mesh it and analyze it accordingly. So this tool helps us to actually analyze and also to create geometries for the real life ground situations. So I will just give you a brief demonstration of it. So this is the GUI of the GTS. So here we can have the model type as 3D, 2D or 2D equivalent, and we can accordingly set our gravity directions. For 3D we have two options of Y or Z, and for 2D the default condition or the direction is Y. And we can have our unit systems. So either we can go by the standard system, or we can also define it according to our wish. So as you can see, it is updated here. And now as you can see that we have the units as for force is lbf and for distance is mm. But again, we can change it from here to go for the standard. So this is a very quick tool for changing the unit systems. So here we have the workstream window, and this is our property window, and this is our works window. This is our task pane, and here we have our menu bar or the main menu, where all the essential features for geometry modeling, mesh generation, modeling, including the loads, boundary conditions, properties, construction stages, etc. are covered. And then the analysis option for creating the analysis case or modifying the analysis control data, and then the post features for viewing your results. Then we have the selection toolbar for selecting or unselecting multiple or single entities. And then we have the tab toolbar for rapid modeling. So all the essential features which are given in the main menu are listed here in the form of icons. So we'll see the operation of a terrain geometry maker. So we can access this option from tools, and then if we click run, then the window for terrain geometry maker will open. I have already opened it. So here we have the terrain geometry maker. We can import the ground contours in the form of DXF files. So this is the side view and this is the top view. And then we can click on the terrain geometry, and we can select our base contour like this. And then we select our rectangle. Okay. And then press OK. So the ground profile data has been generated, and then we just export this surface. So let the name be demo. Okay. And then we go back to our GTS interface, and then again on the tools we click on import. So So we can import this file demo, and as you can see here, now what I can do is I can switch my work planes from here. So my work plane would be XY, and now I wish to create a 2D face. So I click on the option first, make face, and here is our snap toolbar. So I'm using a point snap. So now a face has been generated. Now I will perform an extrude operation. So in the solids tab toolbar, the profile is this face, and the direction can be selected from a 2-point vector going from here till here. And if we click on this option, then the distance between these 2 points will be updated. So it's roughly 530 meter. So I'll just make a solid of a total height 1000 meter. And by this option, we can preview before actually executing our operation. So okay, now I'll just press OK. So my solid has been generated, and I can view and see it in different angles, front, rear, top, or in the isometric itself. And as you see in the workstree window, my workstree window history is updated. So now we have surfaces, and then we have solids, and accordingly for this solid the property is updated. So we have the bonding values for this solid. Also, if I select all and right click, then a context menu opens, and this allows us to see our geometry in various modes. So by default, shading with edge, I can go to wireframe, and I can easily see my surface here. Now what I need to do is I want to trim this solid with respect to the surface. So from these options, I can select my solid by clicking on the solid, and for the surface I can also click from choose my surface from here, or I can also choose my surface from the workstree window. So here, and then I have to give the reference point, and then preview, and then OK. And again, by using the context menu, as you can see, we have a solid representing the actual ground profile. Now going back to the presentation, in our product you can also import various file formats, including the step or the IGS or BREP, and you can also export step, IGS or neutral format files. And as a compatibility feature, we have a frame to solid, where if we have a frame geometry in Midas Civil or Midas Gen, which are again products of Midas software family. So if we have a frame, then we can import that frame into the GTS and subsequently mesh it. Then going to the meshing. So the main features include auto meshing, bump mesh protruding, and manipulation of the mesh. So in auto mesh, we can the program automatically meshes either a solid or a surface or edge planar area, and the type of elements which can be generated here ranges from quadrilateral to triangle, or it can be combination of both. And in the map mesh, The program generates structured mesh elements which are with their edges orthogonal to each other for solid surfaces, a bounded area, or a volume. And the protrude mesh options are used to, or let's say, they help in expediting the process of mesh generation. So with the features like extrude, revolve, project, fill, or sweep, we can quickly create, let's say, a 3D mesh from a 2D mesh, or simply uh, a revolve mesh profile from a 2D mesh profile. And in the mesh manipulation, we can create elements, or we can extract elements. We can also create connections in the form of rigid or elastic links. We can further smooth down the mesh or divide the mesh, and also check for the quality of the mesh as well. But before we begin with the mesh generation, we first need to have a look at the size control option. So basically, if we have a big geometry, and especially in the case of 3D models, then we always have certain parts or certain regions where we are expecting a stress concentration, or where the geometry is irregular. So to get accurate results, we need a finer mesh element size here. And on the other hand, we might not need a finer mesh element size at the boundaries. So what this does for the user is, by using this feature, we can change, or we can control the element size, and eventually this would affect, or this would optimize the analysis time and also the results. So we can either perform give a uniform size for the mesh generation, or by using the linear grading option, we can vary the size of the mesh elements. Uh, also, we can refine our mesh, and according to our requirement, we can either refine it and make it more dense, or make it more coarse. And we can also provide a linear or symmetric seeding for the symmetrical situations, and again, it's a method for expediting the work process. In the automatic surface meshing, we have the three algorithms of loop mesher, Delaunay mesher, and grid mesher. The robust among these is the Delaunay mesher, which is not dependent on the geometry, and it can take care of the holes. And then one of the most robust features of GTS is the automatic solid meshing. And our tetra mesher is capable of generating 2 lakh tetrahedral elements per minute, and moreover, it is capable of including hole curves and points which are present in the solids. In the map mesh feature, we can generate a structured mesh for planar shapes, or and the second figure represents a tunnel lining. And also we can generate a structured mesh with orthogonal elements for a bounded volume. In the mesh protrusion, like I said, this process is used to expedite the work process. So if we have a 2D mesh, then we can extrude it to obtain a 3D mesh, or we can extrude it with respect to a non-uniform offset. And let's say if we have two curves, then by using the fill option, we can generate a structured mesh for these curves. And if we have a mesh and a guiding curve, then we can extrude the mesh accordingly from curve to 2D. And also, if we have a planar mesh, then we can simply rotate it and obtain a profile of a 3D mesh. In the mesh protrusion, we have some more features which include projection from where if we have a 2D mesh profile, then we can project it onto a face and generate a 3D mesh profile. Or if we have two different mesh profiles, uh, then by using the fill option, we can connect them and generate a structured mesh for these two different mesh topologies. By using the sweep function, we can generate a 3D mesh by sweeping the 2D mesh with respect to a curve, and further we can scale it down or scale it up. And one good feature in the mesh protrusion features is that we have an offset function, where if we have a 2D mesh, as in this case is represented by a 2D lining, shotcrete lining, then by using this offset command, we can generate a 3D mesh. So from shells or curved plates, we are generating a solid mesh profile. And in the mesh manipulation, one of the important features is extract element. So if we have a situation of a underground tunnel and where we want to model the shotcrete lining as well, then to model the shotcrete lining, uh, the modeling is inefficient if we use very thin solid elements. So in GTS, we have the extract element option, where the mesh is extracted, in this case for the shotcrete elements, and it is composed of plates or shell. And the advantage is that as compared to using very thin solids, here we can, by using the plate elements or the shell elements, we are restraining some degrees of freedom, so it improves the efficiency of the program. And then in the mesh connections, we can provide rigid links or elastic links to simulate the ground conditions, or we can also create interface elements to model soil structure interaction problems, for example, pile problems. In the manipulation, we can also smooth down our mesh according to our requirement. Then once we are done with the generation of the mesh, then we also need to check for its quality. So for that, we have features for checking the aspect ratio or the Jacobian, which is essential for the quality assurance of plate or shell elements, and or the skew angles. We can also check for the free edges or faces, and absence of free edges or faces would ensure a proper mesh generation. So I will just give you a demonstration of the mesh generation feature in the GTS using uh, a model. So in this, I would open a start file. And in this start file, we already have created curves. And in the properties, we have our ground elements. So if we wish to view or modify our properties, so we can access from here right away and edit. So we can check our input data at any time. Also, if we want to have a quick look, then for the ground, we can see the input data in the properties windows as well. So starting with the modeling, I would first create a solid, using primitive feature. So I can view my solid in the wireframe for easy viewing. And then I want to create a grid face. So I'm giving the grid data. And in this option, we can input a file, a text file for the elevation. So here, as you can see that we have a surface. And then similar to the previous case, I would like to trim my solid with respect to this surface. So uh, I would select my solid, and then I would select my my surface, and I'll keep this reference point as this, and check my preview, and okay. So the geometry can be viewed in any desired viewing frame. The geometry can be viewed at any time using the context menu in any desired option. So we received a query from Mr. Shahab that workstree window is not fully visible. I would like to confirm if it's visible now. Is the workstree window visible to all the users? If yes, then you may reply to us by pressing OK. Okay, now switching back to the wireframe. Now I would use extrude options to create my ground profile. So from the selection filter here, it's by default set to face, so we can change it to the wire at any time. And we can select our extrusion direction as this, and the length input as 100, and click apply. And similarly for this wire profile, I would select extrude it along the global x-axis by a distance of 124 meters. Now I would perform a Boolean common operation. So I can select my Boolean solid, Boolean master as first solid, and then my tool solid. So okay, uh, if we check for duplicates, then there are no co-faces here because our solid is not embedded into the ground mass, so there would be not proper nodal connectivity. So for that, we first need to embed our this solid profile into our ground. So for tool object, I would use my newly created solid. So if we check duplicate again, then As you can see, we have yellow colored core faces here, and this would ensure proper nodal connectivity. Now I would like to extrude my cut profile, which would basically cut my this ground solid into two parts. So first I need to extrude it along the global x-axis. So changing the selection filter to wire and selecting this wire, and that direction is global x-axis and the length is 124 meter. So once I make it, this would be a shell profile. So now I can divide my solids with respect to by using this shell. So what I need to do is that I need to go divide solid by surface, and I need to select my solid. Okay, and then I need to select my tool surface. So the shortcut for shell is H. I select my tool surface, and then the neighboring my neighbor to this solid and to this shell profile is the ground solid. So because this would also be divided, so I will also select this, and performing the divide solid by surface operation, we'll be able to see the results. So as you can see here, we have two distinct solids. Now one of the solids, extrude D3, is not useful for us. So by just pressing the delete option on the keyboard, the delete key, I would delete this. So now this is resembling more of a tunnel profile. Now what I need to do is, if I want to create my blockheads for this tunnel face, then I would just simply check off my my main ground solid, and going for the divide solid by surface option, I would select these two solids, and I will just by simply scrolling my mouse, I can zoom in or zoom out. So this time I would choose a 3-point plane. So my first point is this, second is this, third is this, and now I have different solids. So if I want to assign different properties here, then that would be useful for me. This operation would be useful for me in that situation. Now after performing this operation, I need to generate my tunnel profiles as well. So again, I would use the extrude function, selection filter as wire, and select my wire profile representing the tunnels. So for your ease, I would just zoom in. Just a second, it's a bit zoomed in, so multiple entities are being selected. Okay, now after selecting this, I would select my extrusion direction, and I'll give my distance as 100 and press OK. So if I check on my box, the ground solid, then it would look like this. Now after having this, I would again divide my these solids, my tunnel solids and the ground solid by the shells of these solids, of the tunnel solids, again to ensure a proper nodal connectivity. So I would use the divide solid by surface option, and this time I would select my solids as the total 3 solids, and my tool surfaces this time would be a shell. Okay, and I'll press OK. So once I have this, uh, my workstream window for the geometry is being updated automatically. Now what I'm seeing here is that I have some solids which are extra, and we won't be needing them, so we would remove them. So uh, this would resemble the opening of a tunnel. So we have the opening of the tunnel. Now I would switch my work plane to the back of this geometry, and using the view toolbar, the shortcut for switching the work plane is Control M. So I would make a 3-point plane. Uh, the importance of using this option is that if I want to create a 2D geometry, then that can be created only on a plane. So, and if I want to create it here, then I need to switch my work plane because I want my XY to be oriented like this, and I want my Z to be parallel to the length of the tunnel. So now I would go normal to the work plane, and then create a rectangle profile covering the tunnel solids. As you can see here. Then I would translate this shape. The direction can be chosen by a 2-point vector or by a global y-axis. And then I want to make a uniform copy at a distance of 10 and 5 times. So, okay. The direction in this case would be selected in the reverse way, like this. And if I check the preview this time, okay, this time is fine. So I'll press OK. And this shape here is again of not of a modeling importance to us, so I would delete it. Now I would invoke again the divide solid by surface. So I'm dividing this so that if I'm having construction stages in my modeling, then I could activate or deactivate my tunnel solids according to my construction stages. So the solids which I want to divide this time, they are the tunnel solids, the 4 tunnel solids, and the surfaces are the rectangular surfaces, and the neighboring solid is the ground solid, and I'll press OK. So if I go to my isometric view and check for my duplicates, then as I can see here, we have proper co-shapes here, which would ensure proper mesh generation and nodal connectivity. And also, for now going to the mesh generation, we can provide seeds here. So there are various options of providing seeds, including interval length or the number of divisions, or linear grading, or hyperbolic tangent. So interval length here, I would keep the interval length as 4, and I would choose my edges like this, and click apply. And then I can also provide a linear grading to these edges. So to provide a linear grading, the size varies linearly. So I can have a larger size element at the boundary and a smaller size element near the tunnel. So rather than changing my element sizes from here, I can use this option, select reverse edge. So I would just need to input my input data for once, and the profile would be made accordingly. So let's say if I have a start length of 10 and end length of 4, then this is my direction. The 10 size would be here, 4 would be here, and if I choose the reverse, then 4 would be here, 10 would be here. So I'll press OK. So if I switch to isometric and select all and invoke the context menu, I can see my mesh seeds like this. And again, if I want to hide them, I can hide them as well. Then we have the option for auto meshing the solids. So I would keep the element size as 10, and from here we can select multiple or we can select attributes, and if we need to define a new attribute or change a property, then we can do it from here. So in the advanced options, we can refine it, or we have the option for merging the nodes which are within a tolerance distance, or generating higher order elements using mid-side nodes, and so on. So just going by the default options this time, I would select my solids, all the solids, and press OK. So for the sake of saving time, in the meantime, we can go for our presentation. In the properties, we have element type of truss or embedded trusses for taking the uniaxial forces, and beam and nonlinear beams for uh, for axial forces, moments, and shear forces, if you want to consider them, or tension only or compression only elements. Then we have in plane type plate elements, gauging plates, uh, especially if you want to see the moments for the solids which have a material attribute as concrete, or geogrids, plane stress elements or the plane strain elements for 2D, and axisymmetry elements. In solid we have solid, and in others we can create point spring, metric spring elements for dynamic analysis, or interface elements for soil structure interaction, then rigid links or elastic links. We can also create pile elements, 3D pile elements. The beauty in Midas GTS is that in the 3D pile elements, the interface element is automatically created. So we don't need to create an interface element again for taking account of the soil structure interaction. And both the nonlinearity at the pile tip and along the length of the pile is taken care of. So the GTS provides linear and parabolic types for a plate, plane, stress, and solid elements. And all the elements can be created in three ways, either through the mesh operation, like auto map mesh or mesh protrusion, or we can manually create them in the GUI. And we can also import the mesh data from the other programs. In the material models, we have the material models of linear elastic, von Mises Tresca, Mohr Coulomb for elastoplastic, and modified Mohr Coulomb for considering the softening and hardening. And we can also define a user-defined material model in our product. Then we have the boundary conditions. So in the boundary conditions, we can normally create support conditions or transmitting boundary conditions for 2D equivalent linear analysis. And we can also create a nodal head, nodal flux, or surface flux for seepage conditions. We can also input unsaturated property function, and we can create non-consolidation conditions, draining conditions, and failure surfaces for slope stability problems. So in GTS, the boundary conditions are applied can be applied both to the finite element and the geometry. So in supports, we can create a normal support restraining the translation degree of freedom in the X direction, global X. And similarly, we can, at the bottom of the mesh set, we can restrain the translation in the global X and global Y. So this is the end result if we use the support option. But on the other hand, if we want a quick modeling, and the GTS provides automatic ground support generation option, where the program would automatically search for the ground support conditions and generate the support conditions accordingly. For the seepage case, we can also provide the nodal head or the nodal flux boundaries. Here we are seeing that on the left, the nodal head boundaries are provided, and to the right, we have nodal flux boundaries. We can also provide a seepage phase condition. It could be used where we have an embankment wall where we have no seepage, or we have the no seepage condition across the wall. And for the seepage flux, if we have a seepage flux for the embankment situation, then we can provide a surface flux to the surface flux boundary as well. In GTS, we can also provide seepage boundary function, and this is particularly useful in the transient state analysis. For example, where the reservoir, where the water level in the reservoir is fluctuating. We can also provide draining condition. This condition is used in the areas where we have the excess pore water pressure as 0. And the application areas include consolidation analysis or the seepage analysis. On the other hand, we can also create non-consolidation conditions. We can assign the non-consolidation conditions to the elements which are not consolidating in our model, and the program would treat them as the structural elements and not as ground elements. We can create slip surfaces, circular or polygonal, for slope stability problems. We can also change the element attributes. So if we have, let's say, if we have a change in attributes in terms of hardening of the soil, then for a previously defined condition, we can modify our condition accordingly. And The change element attribute for construction stage. This is a useful feature for construction stages. So if we have a construction stage of tunnel construction, then let's say initially if I have a soft shotcrete lining, and then at the later part of construction stage I want to model it as a hard shotcrete lining, then for the same mesh set I can use this option to change my mesh properties accordingly. Uh, Going to the loads, the normal loads can be provided here in the form of force or moment, and prescribed displacement, pressure or pre-stressing, or line or element beam load. We can also provide temperature loads, nodal mass for the dynamic case, and the GTS has extensive database of functions for the response spectrum analysis according to various codes. And for the time history analysis data, we have a database of 54 earthquake acceleration records. And using this, you can create ground acceleration data or time varying static load or a dynamic nodal load or dynamic surface load for the dynamic analysis. So the load can be applied either to the geometry or to the mesh, similar to the boundary conditions. The advantage of applying the load to the geometry is that, let's say during our modeling, if we are updating our mesh or refining it or deleting it, then the load conditions assigned to those mesh elements would automatically be modified or changed. So to stop that, or to not to let that happen, we can assign our loads to the boundary as well. So here we can define the self weight. For 3D, we can define the self weight in the form either in Y or Z direction. For 2D, the default condition is the default direction is Y, and we can also input the nodal force and moments. We can add the force data or the moment data, or we can replace it or delete it. We can also assign prescribed displacement to the elements or the nodes where we are expecting a rigid body motion. But one caution should be taken here for assigning the prescribed displacement, that the displacement data should be accurate. So what we can do in this situation is that we can analyze a model initially, and from the displacements obtained from the results, we can input those displacements again to the model and rerun the analysis. We can also input the pressure load in the form of edge pressure or a face pressure. We can also assign line load or element beam load. So if we have beams which are connected in a series, then we can simply assign a line load for the whole series of beams as shown here. Whereas if I want to assign loads individually to each beam, then I can use my option of element beam load. So the load would be assigned accordingly. We can also assign the temperature load in the form of nodal temperature or element temperature or temperature gradient. Application of element beam load is similar to the application of a nodal temperature load at the nodes. And one caution which is to be taken is that the temperature gradient load is only considered for the beam and plate elements. So if we have reinforcement, as in the case of reinforced slope stability conditions, then we can input the pre-stressing load for those structural entities. So for truss or embedded truss, we can input the force, the axial force, and for the plane strain or the solids, we can input the stress as shown here. And then we can also input the time history load. So we have the extensive, like I said, we have the extensive database of 54 time history functions. So from using that, we can create ground acceleration load or dynamic nodal loads and so on. And we can perform the linear analysis using either the modal analysis method or the direct integration method. And for the response spectrum load, we have our database covers various design codes, including the Euro code or the Japanese code or the UBC. And from there, we can generate the response spectrum load. So I would just go back to the program and show you that the mesh has been generated here for the solids. So if I use my shortcut for mesh is M, then I can select my mesh and invoke the context menu and hide it or perform other operations. And similarly, I can view my mesh in the form of wireframe as well, as you can see here. Now I would go back to the presentation. In the analysis, in GTS, we can perform static analysis, linear, nonlinear, construction stage analysis, covering the drained or undrained conditions in the ground, or the seepage analysis for steady state or transient state, and semi-coupled analysis using the, for example, using the seepage analysis results in the stress evaluation of a tunnel. Consolidation analysis, slope stability analysis using the SRM and the SAM, eigenvalue or the free field analysis for the dynamic analysis, and we can also perform equivalent linear analysis in 1D, response spectrum analysis, and linear time history analysis. So in analysis, we have to define an analysis case, and we can simply activate, we can simply drag and drop our element data or boundary conditions or load sets into the activated or the deactivated data for the analysis. And this is a very fluid and very smooth operation. GTS has also a robust feature of performing parametric analysis. So in this, let's say in this case, if I vary my K0 parameter for the analysis of a tunnel in a 2D case, then if I vary my K0 parameter, then I can run parametric analysis. And this basically saves time because we don't need to create different models time and again. Also, we can run batch analysis. So we can run 6 or 8 or 10 files and so on, and together. Going to the post-processing features of GTS. So once we have created the analysis, the importance is how easily can we extract the results or view the results. So in a workstream window, in the post mode, we can see our results in the form of a contour, and the same can be visualized in a result table, and we can use this data and export it either to MX Excel, or we can obtain a graph. So in the soil stress analysis, we can obtain a displacement, forces, reactions, stresses in terms of total stress, effective stress, principal stress. For slope stability, we can obtain safety factors or yield ratio. We can also obtain, for strains, we can obtain principal strains, maximum shear strain or David-Torix strain. And for the seepage analysis particularly, we can read the results of velocity, pressure, total head or head gradient. We can also see our contours in different types of contour with mesh or with isolines or with mesh and isoline, contour without mesh, gradient contour and gray contour. So this is an animation representing how we the gradient contour for stress in connecting tunnel. We can also see the results or the contours with either in a deformed mesh or in an undeformed model. So both the deformed and undeformed model or the results can be seen in the post-process option. Then we also have the feature of clipping plots. This feature is useful where we have a 3D geometry, and if we wish to see the results on the inside of the geometry or the mesh, then by using this option we can see our results, and we can also create multiple clipping planes. We can also create on-curve diagrams to view our results, and basically the length or the magnitude of the on-curve diagram would represent the magnitude of the result which we are viewing. So we can create on-curve diagrams in XYZ directions and view our results accordingly. For seepage, we have the special features of viewing the flow path or the flow quantity. And a robust feature is result extraction. So where we can result, let's say, of multiple construction stages and of multiple elements, and the result can be extracted in the form of MX Excel compatible table, and we can also obtain a graph from it. If we have consolidation, then we can visualize settlement profiles in that case. So again, the data can be obtained in the form of MX Excel compatible table, and the data from the table can be exported to graph for better visualization. Then lastly, we have the features of probe and result tag, where we can tag our results in our model and check our results individually for individual entities. So I would just demonstrate some of the post-processing features. So this is an analyzed model for a tunnel with connecting gallery. So here are the options for the analysis case. So as we can see that we have various analysis types, and we can also control our analysis control data from here. So if we switch to the post-processing mode, then this is our post works tree and the results for the various construction stages. So here the results, let's say if we wish to see the results for 3D element stresses, then we can see the results here. So one quick tool is that rather than going from jumping from construction stages to other construction stages by clicking, we can just use this bar for the post data and view the results in our model for different construction stages. And also we can view different results from here. So this is a very easy tool, a very useful tool for reviewing our results. And also in the post command tab, we can view the results either in the form of gradient as we are seeing here, or in the form of a band. And there are also options of viewing the results. So here we have no edge, or we can have a mesh edge while viewing the contours, or the feature edge, and so on. So let's say if we have mesh edge here, then if we use probe result option, then for the soil stress, effective soil stress in the x direction, then we can tag the results here, and we can see the results, and we can arrange them accordingly, or we can obtain the maximum or minimum, and like that. Also, if we wish to see the results in the form of ISO surfaces, so we can create ISO surfaces. So for the sake of saving time, we have already created ISO surfaces here. So as you can see, we can see the particular stress values and the ISO surfaces according to that. And also, if we wish to see our results and going back to the original shape, then we can simply go to the original. And then if we wish to see the results by using a slice plane, then as shown here, by using this slice plane, we are viewing the results here for that particular slice plane. And I can anytime switch back to the original. And talking about the seepage analysis, the special features which we have. So if we have a seepage analysis condition of 2D dam, then in the post, then we can view the results of flow rate or total head. And if I right click on this, then we can generate tabular data. And so the records which I want to activate, we can select from here. So, and so for total head, we can generate the data for that. And at any time, we can export the data to Excel, or we can also create graph. So if the X label is number, then like that we can create graphs for that data. And also for the seepage result, we can see the flow paths. So with this option, plot with contour, so I would keep the result, the contour of total head, and I would see my flow paths. So the flow paths can be generated, and by using this option, we can create multiple flow paths and retain the previous one. So the attributes can be changed from here like this. So by this way we can see the results of the flow path for seepage analysis. And also if you want to extract results, then let's say if you want to extract the results for the total head, then we can switch to the mesh edge and select some random nodes, and then by clicking this we can generate a table for that, and by clicking here we can also see the graph for them. So with this we end our session on the product introduction of Midas GTS. So if you have any questions, you can ask us now. So now the users may ask us questions. One user, Mr. Ahmed, has asked how can we create a user-defined material model. So for that, I would go to my the GUI of GTS. So Mr. Ahmed, if we go to model and then in the properties and material, so we can add a ground material, and in the user models here we have various user models, and you can define a user supply material here and load your Fortran files. The model Fortran files are present there on our website en.midasuser.com. So from here you can create a user defined, or you can input a user defined ground material. Mr. Shaham has asked a question, options for ULS analysis, example EC7, DA1 or DA2. Mr. Shahab, could you please elaborate more on your question? Mr. Shahab, like you have said, like applying different partial load or resistance factors according to Eurocode 7 or design approach 1 or 2. Sir, I would like to say that those conditions are, or those clauses are mainly in accordance to the structures and uh, not not developed for analyzing the ground conditions under the effect of dynamic load. So the partial load factors are not considered because we are dealing two different types of situations. And Mr. Alexei, as you have requested, if you wish to see the demonstration of a real life application problems like diaphragm wall with anchors or a settlement calculation of the building, then yes, such topics are covered in our advanced webinar series. So since this was a basic introduction webinar, so I haven't touched the options of construction stage analysis. So if you wish to learn more on that, you may join our advanced webinar, and you may contact us for the schedule. Mr. Shahab, in a program, we can consider the pseudostatic cell weight analysis. Yes, we can consider that. So if you have any other questions, you may contact us at esupport@midasit.com. So with this, we end our session. We thank you all for joining us for the product introduction webinar on Midas GTS.